Hi everybody, this is Cal with section 15.7, triple integrals. So, the development here is going to follow the development in sections 15.1 through 15.3 of double integrals. Um, and your book starts out with just defining what a triple integral should be. You don't have to pay a heck of a lot of attention to the top of 1041. The idea here is that just like with a double integral where we split a region into a two-dimensional region into a whole bunch of little two-dimensional boxes and then took the height of a function over each of them. With a triple integral, we take a three-dimensional region, split it into little three-dimensional boxes, add up a value of the function in each box, and take a limit as the boxes get tinier and tinier. But you don't really have to worry about the triple Riemann sum at all. We can kind of just like we did with double integrals, we can sort of take a triple integral as we can just sort of take it as something that we can work with in practice. Fubini's theorem exists for triple integrals the same way it does with double integrals, and for a rectangular region, like the one pictured here, the order of integration is totally immaterial. You can do it in any of the 6 possible orders, and those are all valid, which your book says at the bottom of 1041, top of 1042. Example 1 is a great one to work through, and I suggest that you try doing this in a couple of the different possible orders of integration to convince yourself that this works. Now, again, your book defines triple integral over a general bounded region. You do not have to pay attention to the formal definition for how that works. The point is going to be much the same as it is in double integrals, where we can kind of encapsulate the shape of our region by using the bounds of our iterated integral. And again, you shouldn't pay too much attention to this type 1, type 2, type 3 nonsense. What you want to be able to do is instead say, okay, well, if I picture this region, oh, hey, look, z is going from a function of x and y up to a function of x and y. Or, later on, when we get a couple pages in, oh, hey, y is going between a function of x and z to a function of x and z. Or x is going from a function of y and z to another function of y and z. It's going to be for us very important to be able to picture the regions that we're dealing with. And in all these cases, we play a very similar game to what we did with double integrals. We, if we have this picture here of z is going from a function of x and y to a function of x and y, we encapsulate that in the innermost boundaries of our iterated integral. And this devolves then to an integral over the region D that contains the x's and y's that I'm interested in. And then you can, this devolves into a problem that we know how to handle already. So we can see this going on in example 2. I really like example 2. This is something you should be able to do. And I really like this remark that they have in the beginning of their solution where they say it's wise to draw 2 diagrams. One of the solid region E, which they have here to the left in figure 5, and one of its projection D onto the xy plane. This is the x's and y's that we're interested in after we've integrated with respect to z. So, read through example 2 very carefully. You should be able to do similar examples. Then we get into a discussion of how to deal with the situation if we want to integrate with respect to x or y first instead of z. I've already talked about it a little bit. Example 3 is a good example of that sort of thing. And again, I would work through example 3 pretty carefully. Example 4 is a really good example of we have an integral here with bounds that are already set. And what do we do if we want to rewrite it as an integral in a different order? And this is going to be all about drawing the solid and re-encoding its boundaries in terms of a different integration order. And again, this is a process that you should be able to go through yourself. You should pay attention to the pictures that are going on here in figures 11 and I'm sorry, in figures 12 and 13. I will say this is a pretty difficult solid to draw in figure 13. I don't even know that your book has done the world's most excellent job of it. So this is hard. It's okay for you to think that this is hard, but it's still something that you want to work on. This is one of the harder skills in this course, and something that you do want to be familiar with. So do pay a lot of attention to example 4. Then we get into applications of triple integrals. Just like applications of double integrals, you don't need to pay a heck of a lot of attention to this. But I do want you to know that if you take a triple integral of 1 dv over a region, you get the volume of that region. I do want you to know, and example 5 shows that. And I do want you to know that if I integrate the density, I get the mass. Some of the physicists in the audience might want to know about moments, center of mass, centroids, and so on. But we're not going to pay attention to a lot of this stuff for our purposes. And that ties together this section. Example 6 shows some of these applications. But this is going to be of a lot of interest to a few of you and of not much interest to a lot of the rest of you. So that's all I've got for section 15.7, and I'll see you next time in 15.8 and 15.9.